I've been promising to do a bit of work on systems such as this, small four-stroke petrol engines driving vehicle alternator generators. Here's the start of what will be a short series of videos. Quite simply, little petrol engine driving an alternator. I've coupled up the engine throttle to this model control servo so that later on in the proceedings I'll be able to automate the engine control, but for now I can just set that manually. As a power plant for a 5-inch gauge petrol electric Loco, this looks like a reasonably sensible setup. The engine can deliver about 1 kilowatt or thereabouts, and the alternator can probably absorb about the same. Power sources like this abound. It's a very common idea, it's a very simple idea, but the performance of a system like this often disappoints. Unexpected engine stalls are one common failing, and systems usually include batteries, or often include batteries, typically one or more large lead acid batteries. It's widely believed, wrongly, that alternators require connection to large batteries. Engine starting problems also may go hand in hand with batteries, and we'll see why later. But the reasons for these and most of the other problems become clear once we've taken a while to analyse and understand the imperfect system we've created. Making things work nicely comes later. It can be done. So we have a system with an engine and an alternator which might be matched in terms of being approximately the same power rating, but we need to have a look in a bit more detail how they're matched in other respects. This graphic is from the Honda datasheet for the GX35 engine, and the thing I want to bring to your attention at the moment is the trace at the top, the net torque curve. This shows the engine has pretty much a flat torque capability across the operating speed range. That is of interest. In this graphic I've reproduced the engine torque characteristic with a little bit more detail extrapolating down to towards tick over, showing how much the available torque drops away at much lower revs. The green and yellow traces show the alternator load characteristics for two arbitrarily chosen power ratings, and we can see how inconvenient this is. It's not surprising. An alternator is designed to operate over a very wide speed range, so therefore for any given power output it can either produce that power from a low speed using high torque or a much higher speed using a lower torque. Everything works nicely when the torque taken from the engine is just a little bit less than it's capable of supplying. So looking at the green trace, delivering 450 watts, we can see that that's only going to be possible at engine speeds above about 6,000 RPM. Once we get down to the point where the torques match perfectly, we only need a very tiny reduction in speed for the torque to increase, which will reduce the speed, which will increase the torque, and we've stalled the engine. Likewise, looking at the yellow trace, the much lower power level, everything's fine there until we get down to a speed of something like 4,000 RPM. We can merrily produce 300 watts with any engine speed above about 4,000 RPM. But once again, when the engine speed tips to the point where the load torque exceeds that the engine can deliver by even the tiniest amount, then we're on the edge of a slippery slope where the regulator winds up the torque, which slows down the engine, and within a quarter of a second it's stalled. What we've got with our system here really is a system that is better designed for stalling engines than for almost anything else. I've chosen this one because although it's very old, 60 odd years old, it's still widely available, and maybe because it's so old it's very easy to get into, find all the bits that we need to get into, and we can hack it quite easily. Now, looking inside the front of it here, the rotor, right the way inside there's a coil of wire wound on the rotor, and these end pole pieces are like interlocking fingers, so that when there's a current flowing through the field winding on the rotor, this behaves like a multipole magnet, and as it spins, the alternating north and south poles pass by all these wires wound on the fixed part, the stator, and it induces an alternating current in those windings. I guess that's why they call it an alternator. Now AC is not really any good for what we want, but that's okay, because inside the back of the alternator, which is accessible just with 2 screws to remove, we see a rectifier which turns the AC from the stator windings into DC. Incidentally, it doesn't produce an absolutely pure smooth DC. There's a slight ripple on it, a residual ripple from the AC, but more on that later. In the centre here we've got the 2 connections that go through to the little carbon slip rings that make connection to the rotor winding, and this box here, that's the regulator, which is responsible for maintaining the output voltage constant regardless of what the speed of it is. Now, the regulator is quite interesting in that it has got just 2 wires coming out of it. Black wire which goes down to the common ground chassis, the yellow wire which connects to one end of the rotor field winding and also connects to a rectifier output, and the third connection is the actual case of the regulator, which connects to the other end of the field winding. So looking at that as a system, it cannot possibly get any simpler than that. We have got a metal box with 3 connections to it. It's got 1 input, 1 output, and a common which goes to the chassis. Now that's the only possible diagram we can draw that makes any sense of a regulator with only 3 terminals. Just to put a little bit more detail on our system drawing here, the output went to one end of the field winding, which I can draw like that, and the other end of the field winding went back to the same place as the input of the regulator. We could label this as plus V, because that's the output voltage from the alternator. Now, in order to understand precisely what this does, take all the myth out of it, I've cobbled up a regulator here to a bench power supply, and in place of the field winding I've got this low voltage light bulb. Starting from 0 volts, gradually winding it up, we've got to about 5 volts now, and you can see that the bulb is glowing about as brightly as you would expect a 24 volt bulb to glow on 5 volts, not very brightly at all. If I bring the voltage up gradually, as the voltage comes up, so the bulb gets brighter. That's what you'd expect, perhaps 12, 12 and a half, 13, 13.9 volts, 14. Oh, we've come to a very fine threshold where when the voltage reaches a certain level, the bulb goes out, and that's a very sharp, very precise point. And the voltmeter on the power supply is reading 14.52 volts. So what we can say the regulator, what is the regulator then? It is simply a voltage operated switch. It is nothing else. There's nothing more clever about it. There's nothing mysterious about it. And it's hardly surprising, really, when we look at it, that it is such a simple function, because This is a piece of electronics that's 60 years old, so whatever it is, we know it's not going to be that clever. It is a voltage operated switch and nothing more. Okay, well, I think then maybe in order to control our system rather better than the standard regulator does, we need to look at improving upon the regulator. Some of the problems we know about are unexplained stalling of these systems. We also know that I know of a case where a guy had a battery petrol electric locomotive with some big batteries in it. It all ran very nicely except when the batteries were anything other than fully charged. He couldn't start the engine with the batteries being flat, and there's good reason for that. So what can we do to improve the regulator? Well, perhaps the first thing we can do is it only knows about voltage. That's the only thing it can possibly know about, because it's only got the one input for voltage. It doesn't know anything about speed or torque or temperature or anything else. So let's design a new regulator with a second input, and we'll call that one speed. If we can include speed information in what the regulator's doing, then maybe we could prevent the alternator drawing too much power when, say, the engine revs are too low. That would prevent stalling. Might even make life easier for starting with flat batteries. So that's the way we're going to go. We're going to redesign the regulator, and as we'll see, it's not rocket science, it's not even difficult, but we can make a system that doesn't perform very well. We can make considerable improvements, and hopefully we'll see that as it all happens to come together. I'll show you that in the next video when I've cobbled something together along those lines.